Hi everyone, welcome to our OpenValue Düsseldorf meetup. We are very happy that we can broadcast tonight from our studio at OpenValue Utrecht. And well, I would say just sit back and enjoy two interesting talks. The first one is presented by Rachèl Heimbach from OpenValue Utrecht, and he will tell us something about GraphQL and going full stack with it. The second one is delivered by Roy van Rijn. He's director and founder of OpenValue Rotterdam, and he will amaze us by magical music matching with Java. Oh yeah, just feel free to ask questions via the live chat function in YouTube. And well, that's enough from my side. I would say, Rachèl, take it away.
Hello everybody. Like Gerard already said, my name is Rachèl. Welcome. This is my talk about going full stack with GraphQL. So a little bit about myself. I work at OpenValue Utrecht in the Netherlands. I'm currently working as a developer at Rabobank. Unfortunately, no GraphQL for me over there. But in the last years, I've done several projects with GraphQL, and today I'm going to share with you guys the fun stuff, and hopefully you get as excited as I am about this technology. So, GraphQL. So first, small introduction for the people who have never seen it before. And for that, we're going to look at their website. And basically, GraphQL is a query language which lets you describe the data as demonstrated. And the client can get exactly the data shape that he wants. So you get predictable results. I think that's like the thing people know about GraphQL when they hear it. But there's way more of that, of course. And I like this example. You can see in real time people adding the client responses or the requests, and you see the response change accordingly. One of the biggest advantages of GraphQL is, of course, when you are going to batch a lot of resources in one go. And that's usually also the selling point that they, when people talk about GraphQL, right? So instead of having all these separate requests, like in parallel and sequential, whatever, in GraphQL you can just do it in one batch. And that's also what we're going to look at today, how to make a cool GraphQL schema and utilize these functions in GraphQL itself. And before we dive into it, I want to show you the last part here, and where you can see how the left side, which is a client from our query, corresponds to the type definition that lives in the server. And what we can see here is that on the root level you have a resource, and every time you do an indentation you basically go to a different resource. So here you can see that a hero has friends, and from those friends we want to know the name, but a friend also has a home world, which is yet again another resource. And that's okay, how you can see how multiple resources are combined into one request. So, how does this compare to REST? Like many of you probably will be using REST, and here that's the standard. Well, GraphQL changes quite a bit when comparing it to REST. As we know, REST has many endpoints. It's resource-based. So you have your items, slash an ID for a get by ID, etc. Well, GraphQL only has one endpoint, because the query language determines what the data shape will be. Besides that, in REST we also have the full resources. So when I request a resource, I get everything regarding that resource, also the stuff I didn't ask for. And opposed to GraphQL, we can prevent overfetching by requesting exactly what we need, like we saw in the example of the website. Furthermore, we're used to work with status codes, like 400 bad request, 404 not found, etc. Like really gives you the information you need to understand what goes wrong in the request or what's happening. Well, we kind of also lose that information because you only have one endpoint. There might be multiple resources in your query. So a 404 doesn't cut it anymore. So it's either a 200 or something really goes bad. That's basically what happens in GraphQL. And for the last point, in REST you can do versioning, like putting it in your header, putting it in your URL, whatever. And in GraphQL there is no versioning. You support one schema for all your clients, and the data shape should provide all the requirements of your client. So for this talk, I have this small example. I created a small app for a web shop, and to the left we can see our data model. And in our data model, it's a very simple one. You know, we have some item which we can sell, and we have a review that belongs to the item. So an item can have several reviews, obviously, like your web shop does. And we also have a user, and this user can either be the seller of the item or the author of the review. And this is a very simple diagram, as you can see, and nicely distinguishable by the colors. And if we compare that to the actual GraphQL definition you write for this, you see there's quite a big overlap with how you would define it anyways, right? So in our item, we can see our fields corresponding to the blue. We also have some external fields, but you can just define them the way they are, like an average rating, which is a number, and the reviews, which is kind of the reference to the other type. And what I found confusing in the beginning when I looked at this was, what are those exclamation marks, right? And basically an exclamation mark tells you that this value cannot be null. And this means that a GraphQL server will also fail if you have declared an exclamation mark and runtime a null value would pass, it will fail. And the most confusing one is this one, because we have two nested exclamation marks basically. And basically what this states is that we have a collection which cannot be null because of the last exclamation mark. But inside we have another exclamation mark basically stating that the resources in this collection can also not be null, right? So you cannot have a null at your first index or whatever. And for the rest it's pretty straightforward, as you can see. We just use some primitives, not that really exciting stuff, and some references to other data types. What is unique for this definition here is the type query, which is a reserved type by GraphQL itself. And like I mentioned, you only have one endpoint, you only have one schema, but I cannot just request anything from my schema. I need some entry points. And the queries are basically your entry points. So even though I state you don't have endpoints, your query kind of serves as a sort of an endpoint within the GraphQL syntax. So if we analyze this query that's defined over here, we have an item by ID. The ID is mandatory, which means I cannot just leave it out. And I return an item, which doesn't have an exclamation mark, which suggests it can also be null. And that's exactly what we want. So you might be thinking, okay, the schema, this looks pretty straightforward, but how does GraphQL really work? Well, you have your type definition, which is set. And each time a client query comes in, we have to resolve the data that belongs to that the client has been requesting. And that's what they call resolvers in GraphQL. And we have two types of resolvers. And for this one, I'm going to start with the query resolver, which is basically a representation of the type query in the schema. And as you can see over here, we have the item by ID example. And basically what happens when this comes in, the query resolver, the item query resolver gets triggered, and it will just get the data from the service. So in my case, it's like a Java service in your Spring Boot application. It can also be an HTTP call to a different system. It can be gRPC. It doesn't really matter because GraphQL just tells you how to translates the query language into a function for you to fill in. And this is also why GraphQL is such a good middleware as well. So you can just put it in the middle of any system you like, because you're in charge of where to get the data from. So we request an item by ID. We return the item from our service or wherever it comes from. And then basically we're not done yet, right? Because if you have an endpoint for an item, you have a service, you basically only resolve the fields that really belong to the item. So if I look at this example, the average rating will not be in there. The reviews will also not be in there. And the seller as well. Those are different entities, different endpoints, different systems, whatever. So what happens next? Well, before we go to the next part, I'm going to show you a little piece of code of how this will look in Node, in TypeScript. The reason I picked this one is because Node is by far currently the biggest ecosystem for GraphQL. You can implement it in basically any language. I've worked on a project where they did it in Go. People have done it in Java. If you go to the website, you see a whole wide list of all the languages you might like. But by far, Node is mostly supported, most ecosystem, community, etc. So what do you see on the screen? We have an object definition with a query in there. And this is basically an object which will contain all the resolvers. So you can see over here, we have our query and our item. And this is an asynchronous function. For the people who don't understand TypeScript or JavaScript, this just means it will be asynchronous. Pretty obvious. But let's first look at the arguments of this method. So the first argument we're going to skip for now. That's basically the object that has been resolved so far, right? So now we are at the query level. That means nothing has been resolved. It's the root level. It will be empty. So we don't have to look at it. The second argument is basically an object containing all the variables that you put in your query. So in this case, it's an object with an ID in there because we're doing an item by ID request. Well, the third one is the context object in Node implementation, Apollo implementation. And it's basically something you instantiate yourself. You can see it as a poor man's dependency injection. So in other languages, you will probably have different ways of doing this. So in the boot implementation, you will be auto-wiring dependencies as you would. But this is JavaScript, so it's slightly different. And the last one is just an advanced object with some additional information about your query, about the context of the client query, etc., which you usually want to stay away from, unless you really want to do something advanced. And then basically, we resolve the item by doing an asynchronous call to our service. We get the item, and then we can transform it into a different shape if we want to, or just return null. And this is basically it. So depending on your language, the only thing you're implementing on the backend side is our resolvers. So how does this item type gets resolved? That's up to the developer. Then we kick into the second part, because I demonstrated in the previous diagram, we're missing information, right? The average rating, the reviews, the seller, they're all not there. So what happens next? Well, we get to the type resolver. So the item query resolver has resolved a big chunk of the item so far. And since it was not enough, GraphQL will look for the resolving of the actual type itself. So this is not a query resolver, this is a type resolver. And in more particular, the item resolver. And then the same trick applies. We are going to calculate the average rating from the review service via HTTP, gRPC, locally, doesn't matter. We are going to do an item by ID from the review, so give me all the reviews belonging to this item. And we can get the user from the user service, whatever, where it's coming from. It's all in parallel. These fields are resolved in parallel. We get the response. There we go. So how does that look? Well, the query resolver really translates to the keys, the fields defined in your query type. While the item resolver has the same function for the item. So each field of my item type, I can resolve separately. And it's all optional. So I don't have to make a resolver for the ID, the name, etc., because we already have that stuff. But what we're interested in is for the average rating, the reviews, and the seller. And it's more or less the same as we just saw. Except for that this time, the first argument is used to read out the ID of the item, because this is the item that has been resolved by a query resolver beforehand. And now, basically, I have all the means to resolve all the information I need for an item. So if you look at it from the GraphQL side, the query resolver will be called, and then it will evaluate if all the fields are resolved, and if not, it will fall back on the type resolver of the type you are requesting. And then it will do the same trick over and over again up until it has all the data. So for the people who have been paying a little bit of attention, review is also a separate type. So you can imagine that if I'm going to request an item by ID with its reviews and also some information of the review, we also have to resolve that. So if I want to know the author of a review, this is not where it ends. we go another step further, because our item resolver has returned the reviews, but each review needs an author. And this is the trick you will be repeating over and over in the backend implementation of GraphQL. And that's what we see here, the review as an author. And by setting it up in such a way, the client can ask any shape it wants, and GraphQL will make sure that the correct resolvers are called or not. So GraphQL makes sure that you're not computing if not necessary. You can imagine that a setup like this can be very performance heavy, right? So if I'm going to request for an item which has 200 reviews, let's say we're going to fetch them all in one go. And in this setup, this means that if I receive my item, which is one action, let's say like one service call, but then if I'm going to ask for one review 200 times, because of 200 reviews, from a service, you can imagine that's performance heavy. And especially if it's a middleware solution where you're going to fire 200 requests instead of 200 local calls for a review. And to fix that, Facebook created a package called Data Loader, which is the biggest performance enhancement you can do on the backend. And basically what it does, it helps you by calling the data loader instance instead of your actual service. So what happens is instead of calling my review service or backend 200 times, I'm going to call my data loader for that user 200 times. And basically what it does, it will catch all those 200 requests, give you an opportunity to implement a batch method, and then return the items back to the resolvers. And it looks a little bit like this. So I can instantiate a data loader. It just receives a function which receives all the arguments, and since we're doing a get by ID, it's only a string array, so it's not that big, not that complicated. And then I'm going to do a get by IDs, plural. So basically I'm batching now. This would be one HTTP request if this is a middleware solution instead of 200. And it's a good practice to just make sure that all your calls in the back are using data loader, so you can optimize regardless of the size that people are requesting. So that was basically the backend part. Let's talk more about the front end and tooling around it. And one of the coolest tools, I think personally, is the GraphQL code generator. And this was for me personally the game changer for loving GraphQL and working full stack with it. So basically what GraphQL code generator does, as you would guess, it generates code, but it does that by inspecting the type definition that you created and then create, based on plugins, all this type-safe code for your front end and back end. So in this case, we're not going to go through fully, but basically what I configured in a YAML file over here is that I inspect my schema and it's going to generate for me all the types available in my schema. So my GraphQL item over here is a representation of the exact type definition. So my front ends are now strongly coupled with the schema. So you can imagine that if I'm going to change my schema, which you shouldn't do with breaking changes at least, if I would throw this through my pipeline and my clients are rebuilding and regenerating, you'll see that they won't compile. So the build step will fail if your contracts are changed between clients or are not compatible with your client. And this is what I love about this stack, is the strong coupling at compile time. But that's not all. So up until now, we have only talked about how to do this very simple data model from REST, how to transfer that to GraphQL is not really exciting. So now we are going to look into how to really improve the schema and have a professional GraphQL schema, which helps your clients and end users to understand the acceptance criteria of the schema more properly. And as a simple start, we're going to implement pagination, because the example I gave you before, 200 reviews of an item is unacceptable. So the first thing you would think is like, we need some pagination for this. And it's pretty simple actually. So to the left, we can see that we made an extension of an update for the reviews. So instead of just asking for reviews, I'm going to add some parameters inline in the type. This just means that now every time if I'm going to request reviews in an item, I have to specify these arguments, which is the page and the size of the page. And I'm going to return an object which has the reviews in there. It has some paging information and some information about how many pages there are, how many elements there are in total. And if you look at the right, we can see that our query looks a little bit like this. So I want to have the reviews, the first 10 reviews basically, right? Page 0, size 10. And now I have the first performance optimization in the client. Because thing I haven't mentioned yet, maybe you have noticed by now, the performance responsibility doesn't lie fully in the back anymore. It's now spread out over the whole stack, because the backend can only optimize so much if you give this flexibility to your clients, right? So the clients are now in charge of not making any stupid queries. So if they say this query doesn't perform, the backend can look at it and say either like, okay, we can optimize this, or you have to change your front end, because there's not much we can do with this flexibility. And pagination is one of those examples of front-end optimization, which is in general, without GraphQL, also a normal thing to do. Let's talk a little bit about union types. Union types, I think, is a very cool feature in the GraphQL query language, because it allows you to create several potential responses, data shape responses. So this is a real-life example. In my project, I've worked for a web shop before, and they had the situation that sometimes the assortment changed, right? You have an item, and this item is not part of the store anymore. But it's not a normal not found, because it used to exist, and it's actually replaced by a different item. So instead of just giving back 404, I don't know what this is, we had the requirement that people that bookmark this page, if they go to it, they see there's a replacement. So how can you solve that in GraphQL? Well, I can use a union type, and I make a union type called item result. That's what I'm going to return if you ask me for an item. And it will be either an item, which you already have seen, or it will be a replaced item, which is a new type I've defined, which has an ID, a reason of replacement, and an actual replacement, which is the new item. So now my client can ask, give me the item by ID. If it's an item, and you can see those 3 dots, which is a fragment syntax in GraphQL, you say, I want this subset for an item. But if it's a replaced item, I want this information. And together with TypeScript, this is a very strong coupled situation, because TypeScript is smart enough to understand, and we can see that in soon in the response, the difference between the two. So if TypeScript detects this is an item based on the type name you can see over here, it will automatically cast for you and have a strong coupling, which makes your front ends more robust if they're using TypeScript, obviously. So how does it look in the back? Well, the backend also needs to resolve a union, and pretty much it's a very simple function that allows you to determine what the runtime object is, right? GraphQL cannot detect this for you. So what we do here, we have an item resolve. It has a reserved keyword resolve type function. It gets the runtime object, and basically this is a very simplistic check. But if there's a replacement key, then it's a replace item, and if it has a name key, it's an item. So you can make this as complex as you want, as simple as you want. For this example, it's just very simple. So that's where you build in the runtime check by the backend, and GraphQL will take care of the rest for you. So from the client perspective, you'll see this. Either we have an item result containing the item IDs we requested with the type name item, or we get the item result for a replaced item in this shape with this type name, replaced item. And this is what I mentioned by the strong coupling. TypeScript is smart enough to understand the difference between a string literal and a string. So a string can be any piece of text, but a string literal is actually the string value itself as a type. And because a TypeScript generation understands that an item is a type name and replaced item is also a type name, if it detects one or the other, it automatically understands what you're working with. So how does that look in the front end? So I created this little example in React, and basically this component is a representation of the item result. So if I bind an item result to this component, basically we only have to build a switch of type name. If it's an item, this is all autocomplete because, like I mentioned, TypeScript is very smart. I can just bind the result as an item to my item component, and if it's a replaced item, I can read out the reason and replacement and show a notification with the reason of replacement and pass the replacement to the item component instead. And you see zero casting, zero type checking, because the string literal trick I just explained. So you get pretty clean code. So next topic is error handling. I already mentioned you don't have your status codes anymore. So we're missing that key feature in HTTP. So how do we deal with this? Well, one way of dealing with it is by extending your schema with functional errors. And what I mean by functional errors are the errors that you expect, the errors that are part of your acceptance criteria of the thing you're building. I'm not talking about internal server error, bad gateway, all the circumstantial stuff that goes wrong. That's technical errors. I'm talking about functional errors. It's, for example, a not found. If I'm going to request ID 200, doesn't exist, well, it's expected. You have to build something to react on that, right? What happens? So I'm going to incorporate that situation into the schema by adding a not found type. And in this case, I just put in the ID, the not found one, not that spectacular. I'm going to extend the item result union with another type. And I'm going to add an exclamation mark to my return result, because now null is not an option anymore, because I covered all my cases. It's either an item, it's replaced, or it's not found at all. Those are the three cases I support. And this is also what I like about the GraphQL. If you put in your schema, write your schema in a proper way, if you hire a new developer who understands GraphQL, if he looks at the schema, he understands like, okay, an item can either exist, it doesn't exist, or you guys also support replacements, because it's very explicit for your clients when they read the schema. And adding these things to the union is also very easy for the clients to support. They only have to add the fragment over here stating that if it's not found, just give me the ID. Fine. And also in the component, it's pretty much the same. So we already had the switch case with an item or a replace item. And since we just added a new case to the union, the front end can also just add a new case and show a not found component or something similar. That's what I wanted to talk about today, about how the cool GraphQL schema. So I'm curious, any questions?
Yes, there are.
Oh.
So one question is, you can secure REST endpoints. How does that work with GraphQL?
It's a very good question. Just like any other endpoint, you can also secure your GraphQL endpoint, of course. It becomes a little bit more complicated if you want to have some authorization differences between users and endpoints. You could host multiple endpoints for the schema and have multiple schemas, basically. But usually it's a good idea to have just one single source of truth schema, one endpoint. But there is some flexibility in the setup, and you can make it as complicated as you want yourself.
Okay.
Yeah.
Another question is, how about caching with REST versus GraphQL? Isn't it harder with GraphQL?
That's a very interesting question, because I couldn't touch on it tonight, but the front-end tooling around GraphQL ecosystem, like Apollo client, it basically automatically caches everything for you, and you have to manually tell it not to cache certain things. But this is really client-side caching, right? So on the back end, I can imagine having some problems with the caching on the gateway layer, because you only have one endpoint. It's very hard to cache those kind of things. But to give an idea, at the strategy we used in our microservice architecture back then, we put the caching layer and responsibility behind the gateway. So GraphQL itself will not do any HTTP caching, but it's the services behind it who are doing proper caching. So the gateway itself, GraphQL doesn't do anything with it. And that's also a very important thing to note. GraphQL is just a gateway, like an aggregator of resources. You should not be building in authentication. Your backend system should be secure. And GraphQL is just in front of it, basically, and also caching the same thing.
Okay, thank you. Another question. What would you see as improvements for future versions of GraphQL? Or would you say it's up to the tooling to make it even more useful, handier to use?
Well, so that's an interesting question. The funny thing is about GraphQL itself, the query language is pretty robust, but the tooling around it is really shifting like constantly. So my friend Uri it seems like he makes a new tool every week. So they created tooling that automatically changes REST into GraphQL and the other way around. So the ecosystem is really, really evolving constantly. And you have so many people jumping on the GraphQL bandwagon. So I think in terms of tooling, there's no issue that there is too much tooling in my opinion even. But the language itself, not really. They don't support any inheritance in the schema. That's probably done with a conscious decision. But sometimes you have to duplicate a lot of things in the schema which you want to have consistent, but it's not possible. But I wouldn't complain to the developers about it.
Okay. Well, I think that's an answer that was suitable, because we get thanks Rachèl from the one who did the question. Another question. What about mutations? Are you using query and mutation?
Yes. Yeah, mutations are pretty much, you kind of define them almost the same way as you do with queries, except for it's of course resolved in a way different way. So the difference, well, in the back you don't really have that big important distinguish with the query resolving, but in the front end it can be quite complex to use mutations, because like I mentioned before, a lot of tooling does caching and makes sure that your data is limited, the amount of data fetching from the server. But mutations make it very hard, because if you do a mutation, you probably have changed stuff in the back end, and if everything is cached in the front, you have to manually start whitelisting pieces of data that also have to be retrieved again, which pulls a little bit more complexity to the front end, in my opinion. I don't know if that answered the question.
Well, I hope so, and I think
I hope so too.
I think they can find you if not.
Yeah, they can find me. Yeah, I didn't talk about mutations in this limited version of the presentation.
Okay.
You have to subscribe for the full 1 hour version.
Okay. Well, I get thanks Rachèl back from from the one who asked the question, so it's fine, I think. Let's see if there are any more questions. There is a short delay, of course, so we'll wait for a couple of moments. And if not, then I would say many thanks for your talk. We will now pause for a short while, some time to grab something to drink, and we will continue in, let's say, 10 minutes from now. So 7:45, we will start with the second talk, and then I hope to welcome back everybody. Welcome back everybody to our live online meetup. I hope you all prepared yourself for the second talk of this evening. And this one is from Roy van Rijn and is about something magical. So the floor is yours, Roy.
Well, thanks. Hi everyone. Today I'm going to talk about the magic of music matching. That's a mouthful. A little bit about me. Yeah, I do some stuff and I work for OpenValue. And you can find me online on Twitter or on my own website. So, why did I get into programming? For me personally, it was a way to play games. When I was younger, I was allowed to play with my father's first PC. And the only way to really get games was to go to the library and get books like this. And in these books, there were pages filled with source code. And this source code you could type into your own PC, in your own computer. And then finally, if everything compiled and you didn't make any typos and the syntax was correct, you could actually play this game. For me, this was the main reason to get into programming, basically just to play basic games. And this kind of made me understand how things work. I didn't really know how to program. There were some tutorials in those books as well. I followed those. But just by making mistakes and trying to fix them, I learned how to program. But still, software sometimes has the magical moments. The first time I went from a text program to something that could display images, that has logos and photos of people on my computer. This felt like magic. I had no idea how I would program something like that. Because up to then, the only games I made were text-based games. The first time I navigated a 3D world, that was something new. When I played Wolfenstein or Quake, I had no idea how you could possibly program something that moved in 3D. Or the first time a computer spoke to me with a human voice. So the first games that had some voices in it was really magical to me. I had no idea how to make that. Or the first time you took a picture and the computer recognized characters using OCR. Or voice recognition. Initially it was utter crap. Only the last couple of years when Alexa came around, things started to become better. But how do you write a program that listens to your voice and knows what you're saying? Or Google Earth, the first time you found your own home on Google Earth. That was very cool. And maybe one of the last times I had this was when I first used Shazam. By that time, I was already a professional programmer, but I had no idea how you would start to make something like that. So, story time. This all happened about 10 years ago in Maasluis, where I currently live. And I was drinking beer with my friends in the local pub. And one of our friends got out his iPhone and he told me, look at this app. This is very cool. And he started Shazam, and he put his phone up in the air, and there was music playing. The phone listened for a while, and then it told me the name of the song that was playing. My mind exploded. Like, how does this work? How do you write a program that listens to a song and tells you which song? That's something only humans can do. So the next morning, a little bit hungover, I woke up, and I have to know how this works. So my goal that entire weekend, find out how this works, recreate this. So the first thing I did, obviously, was Google. I'm a Java programmer, so I want to do this in Java. How do you listen to a microphone in Java? And it turns out this is actually pretty easy. There is a Java Sound API, and you can access the microphone. And the first thing you need to do is to define an audio format. And this audio format contains a couple of things. It has a sample rate. It has a sample size in bits. The amount of channels. Is there one microphone or do you have two channels? Is it stereo? Is the information signed and is it big or little endian? And you create this audio format and then you can use this audio format to access the microphone, which is rather easy. There's a target data line. And in this target data line, you can open it and you can start it, and then information from the microphone starts pouring into your Java program. It's that easy. So the main thing is there's an audio system, and you can get a line from the audio system and with the given input data, it will set everything up, and then you get the target data line, which is the raw microphone data. This data comes streaming in, and we want to store it. So in this case, I created a byte array output stream, and I would read from this target line, calling the line.read method, and I put everything in a byte array buffer. So at a later point, I can use this underlying byte array to just look what the microphone is giving me. So 2 hours later, finally time for breakfast. I had this feeling, I nailed it. I'm halfway there. I already get all the data from a microphone, so I'm nearly there. So then I opened up the data. What does a microphone actually give me? And this is the data I got, like some numbers. But what do these numbers mean? How does a microphone even, how does your ear even work? How does everything work? Like, everything crumbled. So, looking at this data, I didn't get any smarter. But then I tried to plot this as a graph. So I opened Excel, and I plotted the numbers. This looked familiar. If you've ever
We have a little bit of a problem. Well, the battery is empty of Roy's microphone, so we'll change that quickly, and I think he's back.
I think I'm back. Where did you guys miss me? Where did we get to?
I heard you perfectly.
Go into the chat. Tell me where it went wrong.
Just the last minute, I heard.
Okay,
so,
just the last minute.
Yeah.
So let's just start from breakfast. I had breakfast and I thought I nailed it. I got all the data from the microphone, and the only thing left to do was just match it up and see which song it does. So then I started to look at the data, and I got all these numbers. And these numbers didn't mean anything to me. So what does a microphone even do? What data do I even get in my program? So I tried plotting it in Excel. And if you plot the numbers in Excel, this is what you end up with. And this, to me, was recognizable. If you ever used an audio program or an audio editor or even a video editor, audio is often represented as this, as waves. When you're silent, it's a solid line. When you make noise, it goes up and down. So, it's time for some biology and physics. Sound is basically pressure. So, if you speak or something happens, if you hit your hands, the molecules are moving and they bump into each other, and this pressure wave eventually reaches your ear. And inside your ear, there are a lot of small canals, but there's a small eardrum, and this drum moves side to side with the molecules in the air. And your brain perceives this as sound. And a microphone basically works with the same principle. There's also a small membrane in this microphone, and it also moves side to side. And these numbers that we're getting from the microphone is actually the position of this membrane. So it can go positive or negative. And that's also what you see in the graph. It goes up and down. That's what a microphone does. Now you can also understand what the sample rate does and the sample size does. So if you have a higher sample rate, it just means you get more of these positions. So you get more precision. The second thing you can change is maybe get 7 bits of data or 8 bits of data. So it's just more precise on where this membrane is, because there's more numbers to put in. So these are two things you can use when you're using a microphone and tweak to get a better performance. Turns out though that the positions are basically useless because our ears do the same as a microphone to detect waves, but our head only hears frequencies. So we have to turn this around a bit. If there's a single low frequency, there's a single big wave, and we hear one single frequency, one tone, like one single tone, but actually it's moving up and down all the time because it's still following this sine wave. If we have a higher frequency, it just moves up and down more frequently, so it's a higher tone, but to our mind or to our ears it's moving side to side, but we hear one single frequency. It gets even weirder if you combine like a very low frequency and a high frequency sound. You get some signal that's completely messed up, but our head just hears two distinct frequencies. So just measuring the position of this wave doesn't really tell us a lot, because if you want to talk about what we're hearing, we actually need the frequencies. Luckily, there's a simple way to transform these waves into frequencies, and that's done using the Fourier transformation. Stuart Riffle explained it on his website. His website is no longer online. Luckily, I saved his explanation in his files. But his basic idea is, if you have some audio or some signal, you can look at this as having a bar and a dot moving up and down, which is our membrane. And the image we're plotting, we're just going like this while doing this. If you want to do the Fourier transformation, instead of doing this, we do this. We rotate the axis and then go up and down. So for example, if we take this signal and we rotate it at about 10 hertz or something, you'll get a picture like this. It looks like a spirograph, but you're moving around, and it's basically based around the center. If we would do the same thing, but instead of rotating at a frequency of 10 hertz, we would choose a frequency of, I don't know, 3 hertz, we could end up with an image like this. And you can see that it's no longer center, it's being pulled off center. And the reason that it's being pulled off center is that the frequency 3 hertz is actually in the signal we originally had. So imagine that we are rotating at the same frequency as a sine wave, and we go all the way to there, then we go back, and then we go all the way to there again. So this tells us something. If we do this at 3 hertz and it gets the center is being pulled from the center, that means the 3 hertz signal is actually in there. If we would remove the 3 hertz signal from the original signal and then plot again, it would jump back to the middle. So that's kind of how the Fourier transformation works. It's just rotating and then seeing if that particular frequency is in the audio sample. And if you look at the Fourier transformation formula and you know this information, you can spot all these little things. So to find the energy at a particular frequency, we spin, which is e to the imaginary I, which stands for spin, the signal, which is x, around a circle, which is 2 pi, at that particular frequency, so we're using the same frequency, and then we average a bunch of points along that line. We take numbers 1 to n minus 1, and we divide it. So, cool, now we know how the Fourier transformation works. Do I want to program this? No. So I went to Commons Apache, and there is a fast Fourier transformation. We can just use that. So, listen to a microphone, store all these positions, throw it into the Fourier transformation, and then you get the frequencies. Problem solved. Turns out there's still one big problem, because if you do the Fourier transformation, you lose track of time entirely. It is like if you have a sample of 4 minutes, for example, a song by U2, 4 minutes long. If you do the Fourier transformation and you look at the results, you get all the frequencies in those 4 minutes. It's like the band playing every song at every note of the entire song at the same time. You need the time aspect, but because you do the Fourier transformation and you squash all these waves into the frequencies, you no longer have any idea when these frequencies are happening, which is kind of important if you want to know which song it is. So I was a bit devastated. It was getting close to dinner time. I was looking out of the window, and suddenly it hit me. Windows could be used to solve this problem. We can use windowing. What you do in windowing is, if you have this entire big song, you just take a couple of seconds, or even smaller, you do the Fourier transformation, and then you slide the window a little bit. Then you do the Fourier transformation on this part, and on this part. Now you do lose a little bit of timing information, because it's still a sample being squashed to the frequencies, but we know when it happens. So this kind of solves the problem. In code, we could do the following. We take out the bytes from our microphone, and then we slice it into a couple of slices, and we move this window along, and we do the Fourier transformation, which is just comments met Fourier transformation. And then we have the results. Then we have the frequencies over the song. A better way to do this is not jump over, but just slide a little bit at a time. So there's even more overlap, and you get more time information with having a larger window. If you would combine everything, you end up with this, and this is a spectrum analyzer. So I wanted to create Shazam. First day, I created a spectrum analyzer. And there's a small demo. Headphone warning. Aphex Twin is a DJ who makes music, but it's not really music. Sometimes he just makes a lot of noise, but he hides information in his songs. So this YouTube movie is from one of his songs, and if you would play this song to a spectrum analyzer and you look at the information, this is what happens. There's a small head hidden inside the song. So if you would play this song against a spectrum analyzer, it would show you this image. This, to me, was very useful because I knew this song would produce this image. So the only thing I needed to do was do my Fourier transformation on this sample, plot it, and it should look something like that. And after a bit of tinkering, I created the following. It's not perfect, but you can kind of see the face in there. And even the lines on the side going up. So I knew my code, the Fourier transformation was working, the display not so good. So I'm probably not using the correct logarithmic scale to display this, and my microphone might not be good enough. The above example was made using a professional spectrum analyzer. This was just a couple of hours of Java code. But it seemed to work. So, time to go to bed after the first day. A small recap. What have we learned? Sound is just basically vibrations. Microphones and ears do very similar things. They just move side to side. And accessing this data in Java is actually really easy. There's a whole sound API you can use. There's a problem with the time and the frequency domain. So in the time domain, we have these vibrations, but we want to have the frequencies. But if you just look at the frequencies, you forget all about time. We can use the fast Fourier transformation to actually turn time into frequency. We use windowing to slice everything up and get frequency information and still have a little bit of time information. And if you put all of this together, you get a spectrum analyzer, which was cool, not what I wanted, but it's what I got. So the next morning, got up a little bit sooner. Time to do fingerprinting. And this is actually the missing step to go from a spectrum analyzer to having something that works like Shazam. So I took a random song and I put it in my spectrum analyzer, and this is what came out. And then I did the same thing again. This came out. And these images look very similar. There are obviously differences. There's different background noise. But this is something we could work with. And this is also how Shazam does these kinds of things. It takes this spectrogram image. In my case, I divided it into frequency bands. So the bottom is very low frequencies, and on the top there are high frequencies. And you go to them in time. And I look at the most loud frequencies. So for each slice, I take the frequencies that are loudest at that particular time. And I do this for the entire song, and then you end up with the red dots. And if you would overlap these two things, so that's the code we need to write, and then we can look at the difference between those two things. You can see there's a lot of overlap. And this is actually what Shazam does with the matching. So we have all these slices, which have a lot of frequencies in them. And then we pick the loudest frequencies across these bands, giving us the red dots. Now we compress everything down to just 64 bits. And then we store this in a single long value. So in my case, you can see in the top there are these 4 loudest parts, which is the 1, 1, 1, 1. Then there's not so much loud parts, and then there's 1, 1, and another 1, 1. So this slice of frequencies is actually encoded as a single long value, and the entire song is just a list of these long values. So it makes this fingerprint for a particular song very small. And there's another trick we can use, which is doing hash lookups. So how do I create a library of these fingerprints? So this was back in 2010. I didn't have Spotify at the time. I had my huge MP3 collection, which everybody had. So I used these 3 tools, which plug into the Java Sound API, and then you can decode MP3 files and access them the same way as we could access the microphone. The only thing left to do was actually harvest everything that ends on .mp3, and this was my 2010 code, which I would no longer write like this. I would use the new I/O, which is much, much, much smaller. Go through my library, everything that ends on .mp3, capture the audio, and create this list of longs. So now I have 3,000 plus fingerprints. I have a method to capture these fingerprints from a microphone. The only thing I need to do is listen to the microphone, get these fingerprints, and look in my database which one it is. That seems pretty manageable. So if we record and we get the following fragment, these longs, I do a hash lookup. And hash lookups are very fast. So my entire database of all the songs is just a collection of hashes with a single long value. And for each thing I record, I can do a single hash lookup and get all the matching songs. And if I do this, and I can even get the offset into the song, which is also important. So I do this for my recording. I do a hash lookup, and I look at all the matches. And if a particular song jumps out, then I say, well, I've got a match here. So, for example, we do 100 hash lookups, and 80 of them give a particular song. That's more than enough to say it's probably this song that's playing in the background. So we also have some quality measurement here. And just in time for dinner, I had my working Shazam clone. And I'd like to ask Gerrit to do a pub quiz. So we can actually demo this and do a pub quiz at the same time. So first I'll stop this. And I'll run my matcher. And next, I've got my computer. At the moment, there are 500 songs from the Rolling Stone magazine. The top 500 songs are indexed on my machine. There are actually 17 songs missing, which I couldn't find or couldn't download, or it wouldn't process. And I've got the playlist on my phone. So Gerrit, are you ready to do this? I'm going to play a song, and let's see who's faster, my computer or you.
Camouflage, Beastie Boys.
Sabotage.
Sabotage, sorry.
But the computer was a little bit faster. Let's do the next one. Still hasn't got it. You can still win.
Very known song, but I don't know the title.
The computer knows it. The computer knows it.
Yeah.
So next one.
Kiss, Prince.
Yes. It's 2-1. It's in the top 500. I can't help it. But my computer is telling me that's Jackie Wilson. You already recognized it. My computer has it. Sorry.
I don't know.
The Shazam clone has it. Sorry. Come on, something you can know. This one, you know this one. You know this one. The computer still has it, doesn't have it.
Madonna, Love is a Mystery, Like a Prayer.
Yeah. You got this one.
Yeah? Okay.
Yeah.
So it's 10-2.
Yeah. So it actually works amazingly well. It can recognize the songs, and I can just play some song. And if you give it enough time, I can even at the same time talk, and often it will just recognize it. Yeah, I'll stop. So this is the first demo I would like to do. The second demo I want to do is taking this concept and doing even weirder stuff. So in this case, I've got my program here. And right now, it's actually listening for a particular movie soundtrack. And in this case, it's the movie Rush. Rush is a movie about Niki Lauda, Formula 1. It's a cool movie, and I happen to have the MP3 file of the entire movie. If I now go to YouTube and I look up some random scene from the movie, pick a number, 1, 2, 3. 3, the third one. So now I play this particular sample. And at this moment, I can stop my phone because my computer not only recognized this, it can continue playing it. So right now it's playing the sound at that particular moment in time. So not only can you recognize songs, but you can also recognize where you are in a song. And you can actually match this up, which is very useful in some cases. So let's go back to the presentation and look at some cases like movie alignment. Can you do duplicate song detection with this? Absolutely. This is the first thing when I had my entire MP3 collection. I ran this algorithm on all my songs, and it had a lot of songs that were on 2 albums or on collector's albums, and even some songs that had the original version and the live version, and it would say this is the same song in about, it's 90% the same. So you can totally use this to detect songs. Another idea I had, which I haven't implemented yet, is the alignment of subtitles. So if you download a movie and you download subtitles in an SRT file, they have a timestamp. But this timestamp references one particular movie, and sometimes the movie just starts later, and then the subtitles don't align properly. But if you would use the audio track to sync this up, it should always be perfect. No matter where you are in the movie, it should detect it and the subtitles should work. Because you can detect duplicate songs, you can also use this for copyright infringement, and I'm pretty sure YouTube is using the same thing here as well. Speech recognition, I don't think you can use this particular technology to do speech recognition. So, recap of the final day. You use fingerprinting to find your match. Hashes are incredibly fast, so even if you have a database of millions of songs, because you're doing a hash lookup, it's very direct, and you can distribute this over a lot of machines and get your results back. So this scales very easily, and that's probably why Shazam is so incredible. It's very cool technology, but it's not impossible for humans to program something like this, which I felt like it should have been. There's still loads of room for improvement in my code. It's basically a couple of weekends of work, and then I dropped it. But yeah, I'm pretty sure if you give it enough time, and yeah, you can make this much better. But in the end, after one weekend, I had a working music matcher, and it can beat you in a pub quiz. So that's about it. Are there any questions, Gerrit?
Yes, there are.
Awesome.
First of all, there are lots of memories from different people about elementary school and typing codes for entire days and recording programs from radio.
Yeah.
But there are actually a
I
couple
never
of...
did that.
No?
No. I never had my tape recorder actually listen to. I know it exists, but I've never done that.
Would be interesting if you could write the code from listening to the recording effect.
Who knows?
Yeah. A question. Got a question. Where is it? Could you potentially also recognize individual singers in a song?
Ooh, I don't think so, because it looks at the whole of the song. So it looks at all the particular things that are loud and not loud, and it creates basically an image of that, and that's what it matches. So maybe you could listen to the frequencies and the harmonics and maybe detect if it's. I don't think so.
No. Okay.
You could, but I don't think so.
The other question is not about the singers, but maybe you can say something about that. Can you recognize birds by their sound?
That I know these applications exist. That you can just hold it up. I think that could work better, but only if they play the same songs. And some birds do, but most of your birds sound differently. Maybe.
Yeah.
Give me a big data set and I'll try it.
Okay. So for the one asking the question, just deliver a big data set and you'll get the answer
find me on Twitter.
later on. Okay, let's see if did I miss any questions? I don't think so. Lots of reactions of people who think it's awesome what you did, so that's positive.
It feels awesome, and it kind of takes the magic away. But yeah, it's still when I open this app and I can just do it again. It just, for some reason, I still like the fact that it works, and it still amazes me that you can just play some song and it matches. Yeah. This is the perfect toy.
I'm so happy to be here tonight.
Blues
Yeah.
Brothers.
So glad to be in your wonderful
Or is this
Solomon Burke.
it's the original version probably?
Yeah, it doesn't work. Next. Yeah. So it just it is magic. Any other questions?
No other questions. No other questions.
Okay.
So,
Let's wrap it up.
Yeah, many thanks to Roy and of course Rachèl for these two great talks. I really enjoyed it, and I think, or in fact I'm sure, that I'm not the only one. And these talks will be available on our OpenValue YouTube channel, so you can look them back as often as you like. it's worth to take a look at the channel anyhow, and to subscribe to it, and of course like the videos. Many interesting talks and presentations can be found here. Well, that leads me to a last thank you for joining us tonight. Don't forget to tune in on Wednesday evening. We've got 2 great talks then. 2 great talks by OpenValue, and I would say cheers and have a lovely rest of the evening.